second. Okay, so hi everyone, welcome back. So we're happy to have with us the second mini course this week by Evita Nestoridi. Will tell us about mixing time bounds, cutoff, and limit profiles for Markov chains. And a quick note that the lectures will be Monday, Tuesday, and Thursday. There was a typo on the website earlier, which is now fixed. So it will be at this time, Monday, Tuesday, and Thursday. So without further ado, Evita.
Thank you, Omer. Thank you so much for the introduction and for inviting me. So I don't find Zoom talks less awkward to give. So please feel free to interrupt and ask questions. I prefer this to be a discussion rather than me talking to people that I cannot see. So indeed, the main topic will be mixing times for Markov chains. And I want to give you the plan so that you can decide which day to skip or not. So I want to give some short arguments, basically. I want to keep it simple and short if possible. Oh, wait, there's already a question in the chat. Yes, indeed, you can unmute to ask questions. Thank you, Omer. Okay, so the plan is indeed to give short arguments for hopefully important questions in Markov chain mixing. Lecture 1, which is today, is going to be about lower bounds. So in my experience, people don't talk that much about lower bounds. There is one usual technique due to Wilson. That's not what I am going to be talking about today, though. Lower bounds, sorry. Lower bounds. And in particular, I will focus on two models that share a similar technique when it comes to lower bounds. So the Ising model on a finite graph. That is, as we will see soon, a very popular model coming from statistical mechanics. It's used to study magnets. And then the second one will be the Zetlin library, which is a specific card shuffle that is very popular in computer science. Then this is lecture 1. In lecture 2, so lecture 1 is going to be the most probabilistic one. So I wanted to give you something more intuitive today to see how one thinks about mixing times. Lecture 2 will be more combinatorial in some sense. We're going to be considering L2 bounds. So we're going to be using the spectral information of the transition matrix. I'll explain everything one needs to know. And there's this famous L2 bound technique that people use whenever they can, mainly for upper bounds now. And I will be applying it to the non-backtracking random walk on Ramanujan graphs. For the experts, this is not the traditional non-backtracking random walk. It is another version of the non-backtracking random walk, which will turn out to be reversible. Ramanujan graphs are extremely important, of course, in graph theory, number theory, probability. This will be joint work with Peter Sarnak. And the last lecture, it's again more spectral, is going to be about limit profiles of reversible Markov chains, which is It's a newer question. I mean, people have been already proving limit profile type of results, but I want to discuss a technique that uses the spectral information of the transition matrix. First. And this is joint work with Samuel Lester Taylor. So this is the plan for the next week. I will be giving at least one example here, which will be a Gibbs sampler. As it was introduced in a paper by Diaconis, Carr, and Solowkost. So I just wanted you to have an idea of what I'll be talking about and the applications I'll be discussing, in case you are more interested in some than others. Okay, so then I'll start today's lecture now, which is, as I said, lower bound arguments. And again, as I said, please feel free to interrupt me. So I'll start with a general setup. So we have a finite configuration space. X. Usually we use n to denote the size. I'll try to avoid any confusion. So we will have a Markov chain, and we will have this pxy denote the probability of landing at y if we start at x. And we put some assumptions on these quantities of these probabilities. We want the Markov chain to be aperiodic, first of all, without, I will avoid defining a periodicity. I'll just say that the Markov chains that I'll be considering in my lectures satisfy that we stay fixed with some positive probability. This helps us avoid, being on specific states only on even times and being on other states only on odd times, for example. So I don't want to say more about this. And then we want xt to be reducible, meaning that we want to be able to reach any state at some point with positive probability. And so under these assumptions, we have the following. So if we collect all the information in one matrix, so we collect all these probabilities in one matrix, that is the transition matrix. Then the xy entry will start to the part of the teeth power of this matrix will converge. So basically this will be giving the probability of moving from x to y after t steps, just to understand what this matrix does. And under these assumptions, there is a probability measure pi on x. So that this converges to pi of y as t goes to infinity. And under these assumptions, we also have uniqueness. Okay, this is a convergence theorem. And we want to understand this convergence. Just to have a better notation, I might put the starting point down there. So, sorry, this is a y. Just to make it clear that if we sum over y, this is a probability. We have to land somewhere. So we usually study this convergence with respect to the total variation distance. So if we indeed have a starting point of the configuration space. dxt is just 1/2 of the L1 norm. So total variation distance is defined as 1/2 of the L1 norm of these two measures. Okay, and usually we consider the worst case. I do want to say the general setup today so that we have it for tomorrow and Thursday again. So when we talk about total variation distance, usually we mean the maximum over all starting configurations. And so the mixing time, which is the first notion and the most general notion of this lecture series, is that if you give me an epsilon, I should tell you how big t needs to be so that this total variation distance is less than epsilon. So it's the first time so that dt. So basically we have a Markov chain on some sort of configuration space or a graph or so on, and we want to get lost with, meaning that we want to really look like a specific measure. How many times do we need to walk on the graph in the configuration space and until we are very, very close to being distributed according to pi? This is the question. And it's very intuitive in some Markov chains, like in card shuffling. You really want to follow a rule, shuffle your cards, for example, and you want to ask how many times do I need to do this so that the deck of cards, for example, is very, very well shuffled. And this very, very well shuffled means that there is an error, but I can decide what this error is going to be. Okay, so this is the general setup. And now I want to focus on the Ising model, meaning that now, let me highlight it a little bit. So now the configuration space, X, is going to be well, let me start with setup slowly. So we have a finite graph. V is the vertex set. And N is the size of the vertex set. And E is the edge set. And we'll write X adjacent to Y to indicate that XY is an edge. Okay, for XY in the vertex set. The configuration space now is plus and minus 1 to the V, meaning that each vertex will be assigned a spin, plus or minus. So that's why I wrote it like this at first. Okay, and we want to understand the following measure. So if we take a configuration in X, the probability measure, the mass that it will have, it will be given by the following quantity. So e to the minus beta, beta is a specific parameter. We sum over all edges the product of their spins. And of course, to make this a probability measure, we will need to normalize. So I do not make up this measure. This comes from studying magnets. So physicists want to understand this measure. And there are different questions that one can ask. But in particular, to understand this measure, first of all, we notice that there is this partition function over here that people study a lot. Like I cannot give you a description right now, but to get our hands on the properties of this measure, one can define a Markov chain that converges with this measure. Okay? So, and how do we do that? We do that with global dynamics. So, oops. So the way that we define the Markov chain is that, oh, sorry, there we go. I keep on touching the screen. We pick a vertex uniformly at random. Meaning, wait, we start with a specific configuration. We start with a configuration in X, and we want to take a step. So we first pick a vertex uniformly at random, and we want to update the spin on this specific vertex. So let's call this vertex V. We want to move to sigma plus V or sigma minus V, where these things are defined as follows. Everything else is the same. So if you're not at V, you have the same spin. So if W is not V, you have the same. And then you have either plus or minus if you are at V. This is the definition of sigma plus minus respectively. Just to make it more clear, here, the plus goes with the plus and the minus goes with the minus. And the way that we move is that we condition on everything else being as it is. So we move to sigma plus V with probability, the stationary measure that we had before, so the measure that we wanted to understand earlier, so sigma plus V divided by sigma plus V, pi of sigma plus V plus pi minus of sigma V. So this might look like an odd definition. This really just means put a plus on V, conditioning on everything else being as it is. Okay, but with respect to this measure, the reason why we define it this way is because this Markov chain has a stationary measure pi, the measure that we wanted to understand. Okay, so one of the main properties is what we call reversibility. So if we can check this identity, that the probability, so if we choose the starting configuration according to pi, and then we take a step with respect to the transition matrix, this is equal to having chosen sigma prime with respect to the measure pi, and then take a step and land at sigma. And whenever we have this property called reversibility, then pi is a stationary measure. So because we are also a periodic and irreducible, we will converge to pi. So certain properties of the Markov chain will pass on to the measure. Okay, and in terms of mixing times, people have been mainly considering specific graphs like the complete graph, the lattice, and so on, and they have been trying to get really, really sharp answers in terms of mixing times, you know. That's not what we're doing today. We're not going to get a sharp answer. What I want to present is a result. So theorem, which is a uniform lower bound. So no matter what your graph is, no matter what this beta is, I want to present a lower bound on the mixing time. So the first thing this is due to Ding and Perez, will be that if t is 1/2 n log n minus Cn, then the total variation distance is big. I'm not going to write the error that they got. Their error is better. I'm going to write it a little bit modified, just because that's what I'm going to be proving today. But I want to be honest, saying that they don't need this 1/4, I think. Let's also put equality. And in particular, the second part, which is mainly what I am going to be proving today, is in terms of the separation distance. So I'm going to write the result first, and I'll tell you what the separation distance is in a second. My pencil dies every now and then. I hope that's not a big issue. So what is this ST? ST is defined differently. It's the maximum over all starting configurations and final configurations, X and Y. It looks like the L infinity norm, but it isn't. It doesn't have, it does not have the absolute value. Okay. So, and I'm going to tell you in a second that part B implies part A. And this is why we are going to be focusing on part B. Okay, so the usual way to use the separation distance actually, so the standard result is for upper bounds, not lower bounds. So both things here are going to be due to Aldous and Diaconis. So the first one is that the total variation distance is always less or equal than the separation distance. Maybe at the end of this presentation, I might talk about this, maybe not. But the second one, and this is what we're going to be needing. I always mess up this, there we go, this inequality, is that the separation distance after 2t steps is less or equal than 4 times the total variation distance, but this only works if the random walk is reversible. We're lucky the global dynamics, I told you, on the Ising model is reversible. Okay, so I just want to repeat that the goal now is going to prove this part B, that, you know, for the global dynamics on the Ising model, on any graph, any temperature, the separation distance is big if we take n log n minus Cn steps. And using this inequality, part A follows. Okay, that's what this part is going to be. So other than reversibility, the Markov chain we defined has another property called monotonicity. And so basically the argument and the theorem holds for any monotone spin systems. Do we have, wait, good. Here, C is positive. Yeah, C is positive. So you need to take less steps than 1/2 n log n or n log n respectively. Thank you. Okay, so yeah, you're welcome. Okay, so the main property that I wanted to tell you about, or at least part of it I'm going to borrow, is coming from monotonicity. Let me change colors. And so the main thing here is that if we have two configurations, X and Y, we'll say that X is less or equal than Y if X of I, so the spin at I is less or equal than the spin of Y at I for every I. Okay? This is an order that we will be playing with. And the property, it's not, all monotonicity is not what I'm about to say, but we will need basically that if we start from the all one configuration, so this is just every vertex having all ones, to the t divided by the stationary measure, this is a monotone function. That's increasing in particular, increasing. Okay, with respect to this order. But I'm going to use something even more refined than this, which is due to Perez and Winkler. And I refer you to this paper in terms of a proof, is that even if we condition on the vertices that have been picked by time t, this holds. So this holds. I will write it more explicitly when I need it. You'll see in a very, very soon. This holds even when we condition on which vertices have been picked, have been selected by time t. Okay, this is the censoring paper. And so now I can, tell you immediately how to prove part B of the theorem. So proof of part B. So the separation distance, remember, was the maximum over all starting and ending configurations of this quantity. So how far away is this ratio from 1? And so I can consider X to be the all ones configuration, and I can consider Y to be the all minus 1 configuration. Okay, and this will only make the separation distance smaller. Okay, but the important thing now is to notice that this quantity, we can go from the all ones to all minus ones only if all nodes have been selected. So if we consider the stopping time, capital T, to be the first time all nodes have been selected, then we do the base formula, and this really says that we can condition on T having happened times the probability that T has happened, plus if we condition on T haven't happened, as I said, it's impossible to get from all ones to all minus ones. So from the base formula here, this is a 0. Okay, and so basically this property of the Perez and Winkler property that I was telling you about says that this quantity here, this is less or equal than the stationary measure of the all minus ones configuration. That is because this is a decreasing function, increasing function, even if we condition on T having happened, and the minimum state is the all minus ones. And both numerator and denominator are probability measures. So if we plug this in, here, so let's take this, put it in here, this gives that the separation distance is bigger or equal than 1 minus pi of minus 1 probability that t has happened divided by pi of the all minus 1 configuration. And this really is the probability that t hasn't happened yet. So this is a coupon collecting argument. The separation distance is bounded below by the tails of the coupon collector's time. And what I wrote earlier, this n log n minus Tn, it really is understanding the tails of capital T. And this finishes the proof of this argument. Okay, so I do want to make a small note and say that this argument does not work for pots. Well, I'm not saying the theorem is not correct for pots. I'm saying this is an open question, because for pots, if we have pots means if we have more than 2 spins. Ising has only minus 1 and 1. What if we have multiple colors? Then monotonicity fails, and we cannot we cannot apply this argument. So, as I said, the main thing that where monotonicity is used is here on the Peretz-Winkler thing, saying that this density function is increasing even if we condition on this capital tau having happened, basically. So increasing means that the smallest configuration is the all minus 1 configuration. And so if we plug in the all minus 1 configuration here, this quantity will be less than 1. And so this is how we get that. Oh, maybe you cannot see what can you see what I'm pointing at all this time with my cursor? Could you see that? Let me do it again. So.
Yes, we can see it.
Okay, thank you. So again, if we plug in here in this dot, the all minus 1 configuration, then we should be getting a value that is less or equal to 1. And so we are using this here. We multiply by the denominator. So just saying that, you're welcome. So for pots, we don't know it, and I think it's a good question. I do want to say that, however, we do know something. So for the Ising, the result was, as I said, due to Ding and Peretz. If we go for more general spin systems that are not monotone, then Hayes and Sinclair have a wonderful paper that gives a lower bound of order n log n that works for bounded degree graphs. And these are the references I am aware of. So just wanted to say that even though this argument is simple, it does not work for more spins. If there aren't any more questions on the Ising model, I do want to continue with a card shuffle that I promised, the Chetton library. And these two models are connected. The arguments, are very similar. That's why I decided to put them together.
So what is the best known for arbitrary graphs for pots?
For pots, what I know is the results due to Hayes and Sinclair that works for any spin system that is for bounded degree graphs.
So that's and there is nothing for general graphs?
To my knowledge. Well, the point is getting n log n. I'm sure you can find something of smaller order that I might not be mentioning right now.
Fair.
Yeah. But if you are aware of any references that I should know, please let me know. But I haven't seen anything else.
Okay, thank you.
Great, thank you. So I want to finish with the Chetton library, which is known as random to top in terms of card shuffling. But I'll do it with waves. So let me just take my notes here. So we have n cards. And so a deck of n cards, we will be calling them 1, 2, 3n. And each one is assigned a weight. WI, let's assume they're all positive and they all add up to 1. And the card shuffle says, pick a card according to this W distribution. Pick, say, card I. With probability WI, move it to the top. Now, like most of us will argue that this sounds like a very inefficient way to shuffle a deck of cards. It takes forever. I mean, it is well-known fact due to Aldous and Diaconis that if we take uniform weights, then it takes n log n steps to shuffle. So that's huge. So we don't do it for card shuffling. We don't really do it to shuffle a deck of cards. This is how our computers operate. So when you have a stack of documents and you want to find a specific photo, click on the photo, then your computer moves it to the top of the pile because in some sense, it's likely you're gonna look for this photo soon again. Okay, so this is a popular model in computer science and all sorts of things. So as I said, I'll just like this. We know all sorts of things for this Markov chain. We know all of its eigenvalues, a thing that was due to Fadaford. Although we'll see tomorrow that this isn't useful in terms of mixing times when we're not reversible. This is not a reversible model, whatever that means. What I want to prove today is something that Jim Phil first proved. So but I am going to alter his argument just because the alteration works for a much bigger class of Markov chains called random walks and hyperplane arrangements. I will not tell you what that is. If you want to see it, you can look at my paper on random walks and hyperplane arrangements. I'll focus only on this very, very specific example. So again, we have the separation distance. And what Phil's theorem says is that for the set-plane library, let T be the first time that n-1 cards have been picked, have been selected. n-1 distinct cards. Have been selected. Then the separation distance, remember this L infinity looking like quantity is equal to the tails of this stopping time. That's Phil's theorem, and today I'm going to prove to you only the lower bound. I mean, I can tell you very quickly how the upper bound works, but I want to focus on how you prove that separation distance is bounded from below, from this tails. And it's very similar to what we just saw with the Ising model. So proof of the lower bound. So again, if we have a specific, so I should say, whenever we talk about card shuffling, the symmetric group is hidden behind it. So a configuration of, an ordering of these n cards really corresponds to an element in the symmetric group, Sn. So for example, when the cards are in order, this corresponds to the identity element of the group. If we swap the top two cards, this corresponds to the transposition 1, 2, and so on. Okay, so the configuration space is now Sn, and now the size of the configuration space is n factorial, just because I said earlier that n will always be the size of configuration space. I guess I lied. Okay, and so now we want to choose appropriate initial and ending configurations so that we bound the separation distance from below. So again, we want to choose X and Y appropriately. And if we have a configuration in Sn, we'll see in a second why we will need to consider the reversal. So X bar is the reversal of X, meaning that if we have this ordering in X, if X is some ordering of the n cards, X bar will be reversing them, putting X1 on the very bottom. Okay, so you flip. And the important thing about this X bar is that to get from X to X bar, you better have picked n-1 distinct cards. So things are very similar to what we were doing with the Ising. So the extra term that Bayes' formula would give us is again 0 if t hasn't occurred yet. Okay. The other thing that is also interesting is that, and again, Phil did something more delicate than what I'm doing now. But as I said, this argument that I'm showing you now is generalized more easily. This quantity, if you know that n-1 cards have been selected, then this does not depend anymore on the starting point. And so now we're going to select this X and X bar. So let's write again this quantity. So wait, let's write this. It was this quantity. So, and this is oh, yes. This was weird. So if n-1 cards have been picked, then I don't care about the starting point. So this means that y is what matters. And this is a probability measure. I am cheating here because on the general setup, when one has this hyperplane arrangement walks, it's much easier to understand the sentence that I'm saying now, that we don't care about the starting point that much. So the fact that this is a probability measure says that there is a y such that ay is less or equal than the stationary measure, pi y, whatever the stationary measure of this Markov chain is. I've never told you. Why? Because they're both probability measures and they have to add up to 1. That's why there is such a y. Now choose x, the starting point, to p y bar. And then we have that st is, so in other words, ax bar is less or equal than pi of x bar. So when we plug these things in the separation distance, using this inequality again, we get that this is bigger equal than the tails of the stopping time that I defined at first. If I should do it slowly, it's because we said this is equal to t having occurred times the probability that t has occurred divided by pi of y. In terms of inequality, these two will cancel out, and then we get exactly this. So it's the same type of thing, it's just that we had to more delicately choose the starting and finishing points so that the same inequality, just like in the Ising model, is satisfied. So the main idea is the same. What Phil did is something more delicate than what I said. He said that this quantity over here is actually always equal to pi of y in this Kirchhoff. This, in fact, gives us the equality, not just this one side that I gave you, because whenever we have such a property for every x and y, this is called the strong stationary time. And the main lemma of Aldous and Diaconis, just to complete the picture, says that whenever you have something like this, the separation distance is actually bounded by the tails of the stopping time from above as well. The reason why I showed you this argument and not Phil's argument is because, as I said, it can be generalized more easily, and it doesn't use any knowledge of the stationary measure, which is rare when we're talking about separation distance. Just uses that it is a probability measure. And so with this argument, I sort of want to finish. I'll just write a note here that the argument I showed you, so the separation distance being bounded above by the tails of a very specific stopping time actually works for random walks on central hyperplane arrangements. Whatever this means is this is huge on combinatorics. And if anyone wants to actually learn about random walks on hyperplane arrangements, I think the nicest overview of the topic is a paper by Brown and Diaconis. There are many more papers, but this is a nice introductory paper. And in this paper, you can learn a lot about the Zeppelin library as well. Okay, if there aren't any questions on the Zeppelin library, then basically I'll finish. I don't want to say more about the upper bound. I'll just say again that the plan for next time is to study now upper bounds. And we will do it only for reversible Markov chains. Where we're going to use the spectral information of the transition matrix to bound the total variation distance using the L2 norm. And we're going to be applying that on the non-backtracking random walk for Ramanujan graphs. So I'll stop here. Thank you very much for your attention.
Okay, so yeah, let us thank Evita. And yes, and we can have questions.